And today I'm going to talk about this topic, transmit beamforming for phased array radars under uncertain occupancy map information. So it's a long title, and this work was done by my student Edoardo Focante, uh, and it was done together with Geethu Joseph and Ashish from NXP. Okay, so the story is as follows. So automotives today have a lot of sensors embedded into them that spit out a lot of data. And based on this data, we've seen forward algorithms that build occupancy maps as digital representation of the environment, right? So Payan talked about one such algorithm using Bayesian learning that takes in point clouds from sensors to come up with a representation of an environment. Okay, so for those of you who just came to this talk, what is an occupancy map? Basically, it's a two-dimensional representation of the environment in this case, and the value that an occupancy map takes at a particular cell is the probability that that cell is occupied by a target. Okay, so it's a probability, so its value can lie between 0 and 1, right? So I call this as a forward problem where you take point cloud information from the past or at a particular time instant and build an occupancy map representation of the environment, right? Now, what we've been focusing on in my group at Delft is the inverse problem, okay? So that is, given an occupancy map information at a particular time instant, how do we take this information right to the level of sensing? Okay, so it's very different from sensor fusion. Sensor fusion is saying let's put together information coming from different sensors, but what we do here is situation aware sensing, which means we take one modality or a group of modalities, get a summary of all these modalities in the form of an occupancy map, and take the knowledge that we learn from an occupancy map right to the level of sensing. Okay, so this requires us to understand the physics of how these sensors operate, and that distinguishes this work. Okay, so let me give you some insight on how you could possibly use an occupancy map to adapt a sensor. So in this case, we talk about a radar. So for those of you who were at the live demo, in the last session, we did do something similar in the context of a LiDAR. Okay, so today I'm going to show you that situation awareness is useful to enhance radar perception. And I'm not going to show just that. I'm going to show you that situation awareness is useful even under uncertainties in the side information. So that's the key point that distinguishes this talk from the live demo that we had in the last session. Okay, so let's say we've got an occupancy map, and let's say the occupancy probability of a certain cell is 1, right? So does the radar need to scan such cell? No, right? Because if it knows for sure that a cell is occupied with a probability of 1, then the radar doesn't need to illuminate that cell at all, because if it does illuminate it and waste power over there, then it doesn't get any new information on the presence of a target, right? So the same thing applies even for occupancy probability of 0. If we know for sure that nothing is present in a particular cell, maybe we are looking at cells above a lake, okay, the radar doesn't need to waste its power illuminating those cells, right? So it makes sense for radars to emphasize sensing regions with high occupancy uncertainty, and we use entropy as a measure of uncertainty, okay? Now, you might wonder, well, this is something that cognitive radars do anyway, right? And there's also prior work in this area that uses entropy-based measures over an occupancy map to adapt beams. Okay? So one such work is from Romero's group, where they adaptively steer a fixed beam, and the steering is done from regions of high occupancy uncertainty to low occupancy uncertainty. So this way, the radar gets to focus on more important regions and then slowly shift its focus to less important regions, right? And we said, well, such an approach makes use of an occupancy map. However, it takes a lot of time for the radar to perform this beam scanning. What you could do instead is you could leverage the full capability of MIMO radars or analog radars to create multi-arm beams that illuminate multiple cells at the same time. as shown over there on the right. Okay, so this is our recent work from ICAS that is reference to. Okay, and today I'm going to show you an issue with this work, a practical issue with this work, and we'll see how to solve this practical challenge using a numerical approach that we propose. Okay, so just to give a summary of what we did in our ICAS work. So the goal was to design a beamformer W at an automotive radar that intelligently illuminates the space around the radar by making use of an occupancy grid map. Okay, so for that, it's important to understand how the physics of the radar work out. So if W is the beamformer applied at the radar, then the detection probability at a cell indexed by r and theta in the polar coordinates is given by that expression over there. And this expression varies from detector to detector. So the one that we have here is for the Neyman-Pearson detector, right? And as you can see, when r increases, so as you move far away from the car, the probability of detection naturally goes down with this expression. And you can also see the beamforming gain term showing up over there. So for a higher beamforming gain, you have a higher detection probability along a certain direction, right? And how do we put together this PD map and the occupancy grid map? So, well, we propose this formulation where we say, well, let's design a beamformer W that emphasizes sensing cells associated with higher occupancy uncertainty, right? So we weigh the PD expression there with the entropy map associated with an occupancy grid map, right? So if entropy is large, that means we emphasize detection in a cell associated with higher uncertainty, right? So this was done under the unit norm constraint on the beamformer. Now let's get to the issues now. So in practice, let's say you go with our ICAS approach. So the car reports its location shown by the blue dot, and then you get to design the beam based on the occupancy map from, this one is from New Scenes. And you get a good enough beam that focuses towards the two legs of the Y lane, right? So if you're approaching a Y junction, you would want to focus along the two legs of the Y junction. And this beamformer is reasonable because it avoids illuminating regions that may be occupied by buildings in the Y, right? So now the first issue that I'm going to discuss is on location uncertainty, right? So this work in our ICAS formulation assumes that the position of the vehicle and the orientation of the vehicle are both perfectly known. In practice, however, there's an error due to localization issues, and this error can result in a mismatched beamformer. Let's see that. So let's say the blue dot is the estimated location and the green dot is the true location. Imagine what happens if I apply this yellow beam designed for situation 1 to situation 2. You may end up in a catastrophic situation because this beam focuses limited amount of power along the main lane, right? So it's important to address this problem of location uncertainty right within our optimization formulation, right? And that's what we are going to do today. And on top of that, we are also going to address the analog beamformer constraint. So earlier we assumed that both amplitude and phase control are allowed in a radar, okay? So for implementation reasons, it may be useful to have just phase control. So let's see how do we deal both these issues. So the first constraint says, well, just the norm of W needs to be less than or equal to 1 for an analog radar. But if we relax it to a phased radar, then we have a more stringent constraint that says, well, the entries of W need to have a constant magnitude, right? And this is something that can be incorporated in our optimization problem. So you just change the unit norm ball constraint to a constraint that looks like this. Okay, it's a discrete valued constraint in practice. And you could employ projected gradient ascent algorithms, for example, to solve this problem. Okay, now let's talk about the main issue. So how do we deal with these localization errors? So in practice, these localization errors are random and they are not known, right? But what we know is the statistics of these errors. For example, you could say that with 99% probability, the localization error that you have is within a 2-meter ball, okay? So once you have this statistical information, okay, based on the physics of localization and orientation estimation sensors, you can take those statistics right to our optimization problem and then come up with something that is more reasonable in practice, okay? So let's take a look at an example. So let's say for a particular realization of error, you have an occupancy map shown above, and for a different realization, you have an occupancy map shown below, right? So as you can see, these occupancy maps are slightly shifted versions of each other, and there's also some innovation on the right? So what we could do is, instead of taking one occupancy map and designing the beamformer for that map, and then suffering later on due to mismatch, we could consider the statistics of these errors and then compute an average of these occupancy maps. And we call that as an expected occupancy map, right? So as you can see, the expected occupancy map is kind of a blurred out version of what we have for the first map, right? And we incorporate this expected occupancy map right into our optimization problem, okay? And we say, well, let's design the beam considering an expected occupancy map and then take entropy of that expected occupancy map, where the expectation is taken over all possible errors within the localization error ball, right? And then we solve this problem. So as you can see from this result over here, okay, so with a situation aware beam that is agnostic to any uncertainty effects, you end up with the blue beam shown over there, which is focused along one direction. But when you embed statistical information about localization uncertainties, this beam widens to the orange one, right? And that makes sense, because if I'm not sure whether my car is exactly over here or there, I can take an uncertainty window around my position and then kind of blur out the beams that I get for all these positions and come up with a broadened beam, right? So that's very logical. And you can also see from the right that with our uncertainty aware approach, the design beams achieve a superior detection over the conventional design or an approach that totally ignores uncertainty, okay? So the punchline is that, well, situation awareness is useful in adapting sensing, but it's also useful even under practical localization errors for the systems that we have today, okay? And on the right, you can see that we just did a live demo. You can take a look at the video over there if you missed it. So that's for a LiDAR though. So we show how you can use situation awareness to adapt LiDAR sensing. And an extended version of the paper that I presented right now is available on the transactions on radar systems, where we consider the tail of localization uncertainties and not the bulk as in the expectation, okay? So feel free to check it out, and I'll be happy to take any questions at this point.